Welcome back, everyone. Let's continue on in chapter 22 with our discussion of reactions that occur on the alpha carbon to carbonyl carbons. And I'd like to go over halogenation at that position, meaning replacing one of the alpha hydrogens with a halogen atom. And then I'd like to just start to get into the topic of forming enolates and what we can then do with the resulting enolate, such as alkylation reactions. And we'll leave the rest until a future video. So you will recall that an aldehyde or ketone, and here I'm being very generic, is enolizable as long as there's at least one alpha proton. And we've learned that those alpha protons are slightly acidic. And so you can form the enolate of such a species in alkaline solution, or you can form the enol in acidic solution. And that's what we're going to look at first, is forming the enol of this species in the presence of a halogen, either elemental chlorine, bromine, or iodine. Any of those three will work. Fluorine would, of course, not work. F2 is crazy reactive and would no doubt just pull the molecule apart. So, but with chlorine, bromine, or iodine, using acetic acid as a solvent, you will replace one of these enolizable protons with a halogen if there's more than one such proton in the presence of just one equivalent of the halogen. And it should say one way or the other, I would think. Watch OWL very carefully, as always. If there's more than one enolizable hydrogen, and you use an excess of the halogen, in other words, enough mole equivalents of the halogen to replace all of those hydrogens, then you will indeed replace all such hydrogens with the halogen. So here we have an example of such a reaction. I'm using here cyclohexanone just as an example. You could use any appropriate enolizable aldehyde or ketone. And if we treated cyclohexanone with one equivalent of bromine, and again, I could have used chlorine or iodine as well, in the presence of acetic acid as solvent, then you will replace one of the four ionizable or enolizable hydrogens with a bromine atom. The mechanism is shown here in your class notes, and again, the mechanism would be the same if using any other enolizable ketone or aldehyde. We first need to put the proton on the carbonyl oxygen, as we always do, since we're an acidic solution. And the way we know that is by what we're given. We know that acetic acid is an acid, admittedly not the strongest acid in the world, but good enough to undergo some deprotonation in this particular reaction mechanism. And you'll notice that in so doing, we're forming an acetate ion. And to me, carboxylate ions in general are the limit that you can go to in acidic solution. Remember that we've said that in acidic solution, you must not show formation of any strongly basic anions, like alkoxide ions or carban ions. Carboxylate ions, though, aren't strongly basic, but again, that's pushing it to the limit. But we do know that acetic acid, being at least a weak acid, will to some degree in solution give up a proton. And with acetic acid as the solvent, I see no problem with drawing the reaction mechanism this way. We don't have any water, though. This is done in anhydrous conditions, so I think it makes the most sense to use acetic acid as our acid, since we can't use a hydronium ion, because we're not shown that water is present. The only alternative I could see would be to use actually the conjugate acid of acetic acid as the acidic species. In other words, with two protons here. I don't, or maybe one here and one here. I don't think there's going to be any reasonable amount of that form in the solution. It's simply too strongly acidic. I think it makes more sense for each carbonyl compound to pull their proton off of acetic acid as one is needed, And then we can use the acetate ion as a base. Again, it's not the greatest base in the world, but under these conditions, it's good enough when acetic acid is the solvent. So we pull off one of the, in this case, 4 equivalent alpha protons with the acetate ion and form the enol of our ketone or aldehyde, in this case of cyclohexanone. Now, in the next step, the enol is going to react with your elemental halogen, and the elemental halogen is our electrophile. So the enol will act as a nucleophile. Recall in the previous video, we talked about how enols are much more strongly nucleophilic than unstabilized alkenes. And even unstabilized alkenes can react with good electrophiles. But because of the oxygen atom, which can donate electron density by resonance, then we can all the more easily add electrophiles across this carbon-carbon double bond. Once we've done that, we simply have the conjugate acid of our product. We can use another acetate ion to pull that proton off, and we get our halogenated compound. And if there were an excess of the halogen in the mixture, then we would pull off first the next proton, and then one by one the other two. And again, the problem should state what you've got and make it clear, especially if it's a mechanism problem. Most likely you're going to be given the product. So I think any problem, certainly that I write, will, to the best of my ability, make that clear. Owl will be owl, so read the questions carefully. What if rather than a ketone or aldehyde, you've got an enolizable carboxylic acid? These can be brominated too, but it requires harsher conditions because carboxylic acids are just that much less reactive than aldehydes and ketones. The reaction mechanism is actually pretty much the same as for a ketone or aldehyde. However, you will not be responsible for it. The way it works is we need phosphorus tribromide in addition to bromine. And as far as I know, phosphorus trichloride and chlorine will not work. I wonder if perhaps phosphorus trichloride just isn't quite reactive enough. Phosphorus triiodide I don't think exists. So I think this will be limited to bromination at the alpha position of an enolizable carboxylic acid. In any case, the action of the phosphorus tribromide actually is to convert the carboxylic acid into an acid bromide. So instead of OH here, you'll have a bromine, and you'll have that at first. And then, honestly, it goes through pretty much the same mechanism as with ketones or aldehydes. You replace one ionizable hydrogen with bromine if there's one equivalent of bromine, or if it says there's an excess of bromine, then you will replace any and all enolizable hydrogens. And then that's also, because we're going through the acid bromide rather, this is why we need the aqueous workup. And again, that's a separate step. So in real life, you would dissolve your carboxylic acid up in whatever solvent, or possibly not even use a solvent. You might just do it neat in phosphorus tribromide, and then add bromine. And then you would wait until the reaction's done, until nothing further can happen. In other words, until you've replaced all of your enolizable hydrogens with bromines. And then you will add water. And the water will destroy any leftover phosphorus tribromide, which would not be pleasant. Trust me, one tends to get great, disgusting volcanoes puffing reddish-brown gas out of the flask with that. But be that as it may, on paper it's fine. And in any case, after the phosphorus tribromide is destroyed, the water will hydrolyze the acid bromide and go back to the carboxylic acid. That hydrolysis mechanism being exactly the same as hydrolyzing an acid chloride. All you've done is changed the identity of the halogen there. And you can get the brominated product in such cases. Next, we'll cover, in the next video rather, we're going to go over the reactivity of various enolate ions. First, though, I'd like to mention more specifically the still in some sense generally, but a little more specifically, I want to zero in on how it is that we make enolates from an enolizable compound. And what we need is to treat the enolizable ketone or aldehyde in this case with a sufficiently strong base. And as you see in your class notes, such bases include, but are not limited to, the hydride ion. You're certainly familiar with reagents such as sodium hydride and potassium hydride. NaH and KH will certainly pull off a proton like that. Sodium amide, our old friend, NaNH2, will certainly do the same. One base that's very commonly used, and it's not the only such base that's used, is lithium diisopropylamide, or LDA. LDA is the conjugate base of diisopropylamine. And so that's another base that's more than strongly basic enough to pull protons of this type off. It's possible that you can also get away with a weaker base depending on the structure of the starting compound. And we'll get to examples of that in our next lecture as well. And then once you get your enolate ion, of course, there's a variety of reactions that you can do with enolates. They'll react with a range of electrophiles, most of which we'll talk about in the next video. But I wanted to make sure that we understood how to make enolate ions. And enolate ions are even better nucleophiles than enols. And we'll cover alkylation the next time. But since we just talked about halogenation in the alpha position, there's one particular reaction that's special to methyl ketones. And you could imagine that if we started with acetophenone, which is phenylmethyl ketone, so in other words, CH3 instead of CBr3, if one then treated that with an excess of bromine in the presence of acetic acid, you would convert it to this compound, and you will know that that's happened by what you're shown, or you'd be given the tribromo or trihalo alkane, ketone, trihalo ketone as the starting material. But we already know in principle how to make a compound of this type. And as I think of it, you I'm pretty sure talked about this type of reaction in lab back in the old days when we were doing lab in person. If trihalomethyl ketones of this type are treated with base, generally one uses an alcohol as solvent, although simply because it's better at dissolving everything than water. But I imagine the very same thing would happen in water. If we first treat trihalomethyl ketones with alcoholic base or aqueous base, a further reaction is possible. Again, this is special for the trihalomethyl ketones that come from the halogenation of methyl ketones. And again, these do not have to be bromines. Those could just as easily have been chlorines or iodines. And this reaction is known as the haloform reaction because a haloform is one of the products of the reaction. But in any case, if you have a trihalomethyl ketone of this type, this will react with the hydroxide ion that you're given. Again, you'll notice I'm just showing the hydroxide ion. This could say KOH, it could say NaOH, it could just say OH minus. So especially with OWL, read the question carefully. But I'm still seeing disturbingly too many people trying to use species with alkali metal ions in their mechanism. That is, copying the alkali metal into the picture. And you'll notice I'm not using it because it doesn't play any role whatsoever. The potassium ion in this case is just a spectator ion. It doesn't play any role in the chemistry. In any case, with hydroxide ion present, this carbonyl group is of course susceptible to nucleophilic attack. And since we see that we're in basic solution now, it might be that we made the trihalomethyl ketone in acidic solution. But we can then change reaction solutions and move to a basic mixture. And now hydroxide will simply attack directly and form this oxyanion, which is completely fine in an alkaline solution. That anion would be far too alkaline for an acidic solution. But in alkaline solution, we are good to go. That species is very defensible, to say the least, in an alkaline solution. And this lone pair in the oxygen can now fold back in and reform our carbon-oxygen pi bond, going back to an sp2 hybridized carbon from sp3. And it then has two options. It can kick out the hydroxide ion and revert back to the starting material, or it can kick out this trihalomethyl anion, which ordinarily we don't think of carbanions as being good leaving groups at all. In fact, in general, they're just about the worst leaving groups there are. But with these three electronegative halogen atoms, all sucking electron density away from that carbon, we can get this trihalomethyl anion, and it's stabilized enough. At that point, two things are going to happen. Given that we're in an alkaline solution, one of them is that, as we've so often seen, hydroxide ion will immediately deprotonate the carboxylic acid, even though that structure is the same as the product structure we are given. Still, we can't prevent this from happening because we're still in alkaline solution. There's no way to add hydronium ion in our second step in such a way that we do not have to show this happening. Because if we tried to do that, we wouldn't get a complete reaction. It would only react part way and we'd get a mixture. So we've seen cases like this before, where an acidic species is generated in alkaline solution, and thus we must show the further deprotonation. That will get us to the conjugate base of the carboxylic acid that we will eventually get. Another thing that happens, and again, any question wording will make it clear what you have to show. Another thing we cannot prevent from happening is protonation of this trihalomethyl anion, which, even though we're in alkaline solution, the pKa of this compound is going to be way higher than even pH 14. I would put it in the 40s at the very least, maybe 35, something like that. So that's going to pull a proton off our solvent, whatever the solvent is that we're given here. Water if it's water, ethanol or methanol if it's ethanol or methanol. Now, the reason that you can't use this anion to pull off this proton and save yourself a step in that way is because, remember, we're going to have a large excess of hydroxide here floating around in solution. We're just going to get one equivalent of the trihalomethyl anion. So those are largely outnumbered by the hydroxide ions. So I think these two steps need to be shown separately. You will know what to show and in what order to put them based on how the question's phrased. And so at this point, we've got our haloform and our carboxylate ion all swimming around peacefully and happily in our reaction mixture. Then we will add aqueous acid. And if we showed these over the same reaction hour, you'd need numbers. 1 KOH ethanol, 2 H3O+. They're separate steps. We add the alcoholic or aqueous base, and we wait until everything's done reacting. And we get our haloform and our carboxylate ion. Then we add aqueous acid. The first action of the aqueous acid will be to neutralize any leftover hydroxide ion, which there should be plenty. And after that, it will start putting the proton back on the carboxylate ion. So you can isolate the free carboxylic acid, which is a neutral compound. Always remember our rule that you want to aim for neutral organic compounds in your mechanisms and in solving problems. Ions are, in general, very, very hard to isolate. Now, why is this a special reaction for methyl ketones? Well, in the case where, certainly in the case where the halogen is chlorine or iodine, you then would get the corresponding haloform, either chloroform or iodoform. But where you might have seen this type of reaction in lab is if the triiodomethyl ketone is made. So if this is CI3 instead of CBr3, which again you would be shown, or you would be given the triiodomethyl anion or triiodomethyl ketone as the starting material. In any case, when these are iodines instead of bromines, in the end you wind up with iodoform, CHI3, which is a bright yellow solid and quite insoluble in aqueous and alcoholic solution. So this will fall to the bottom of the flask. You'll see this bright yellow solid, and you'll say, oh, I guess whatever ketone I started with was a methyl ketone, because I got iodoform out at the end. So this was used as a chemical test for a very long time. It's not so much used anymore, candidly. We have much better ways of telling whether our compound's a methyl ketone or not, such as carbon and proton NMR, for example. But if you saw this in lab, that's the history behind this step. I'll also mention that iodoform, CHI3, was used in its own right for a long time, quite some time ago, probably 100 years ago, as an antiseptic in hospitals. So that's an example of how it is that these types of compounds react under alkaline conditions. But again, this is a special reaction of the trihalomethyl ketones that come from methyl ketones when exposed to a basic solution. There's, of course, many other reactions that we can have after having formed enolates of this type. We don't really so much form an enolate here, but let's remember that the chapter is on enolate formation and reactions, and so we'll leave those reactions for the next time.